interesting stuff already, so I decided to adapt my talk a bit and cut it down drastically to focus on my main message. So if you like, enjoy the 9 slides that I have. It's not too many. Okay, so what is synchronization? On the right-hand side, you see fireflies in the Americas. On the left-hand side, you see metronomes, 4 of them. And those are oscillating units that start oscillating out of phase. You see the blinking. And if you give it some time, those oscillating units that are coupled oscillators, they start synchronizing. Okay. And why do they start synchronizing? Well, because they're coupled. In the case of the metronomes, they're sharing a mobile platform. And in case of the fireflies, each firefly looks at what the firefly right next to it does in terms of flashing, and so they adapt a bit their frequency and their phase. At the end, they have synchronous phases. Okay. Why is this concept of synchronization important to power grids? Well, maybe I should elaborate on what power grids are. Power grids are hierarchical structures. You have on the top of it, you have high voltage grids called transmission grids that transmit power from power plants to substations. Do I have a? I'm sorry. And then those substations delegate power to lower voltage grids like distribution grids, where then the power is ending up at consumers. So you have 3 elements in transmission grids, which I will focus on in the following. You have generators that inject power, you have consumers or substations that draw power from the grid, and then you have transmission lines. Historically, the AC standard won over the DC standard when it comes to transmission grids. So you usually have rotating machines as generators. You can consider substations also as rotating motors. It's possible mathematically. And what you end up with is a network of coupled oscillators that describes the transmission grid. Each oscillator is characterized by a phase only, so it's phase oscillators. And in 2008, Filatrella and co-workers put up an equation for the dynamics in such a grid. To simplify, okay, on the left-hand side, you have a term that describes the inertia of the rotating machines. Then also a term that is a damping torque, okay? And on the right-hand side, you have the injected or drawn power from the system and the coupling of the oscillators, okay? So imagine, ignore this term here and the coupling term. What happens? Each oscillator will spin with a frequency that is it's given by the power drawn or injected. Okay. If you switch on the coupling, as Joachim Painke has shown in one of his plots, if you crank up coupling large enough, you will have oscillators starting to synchronize. But I'm not talking about phase synchronization, but I'm talking about the frequency synchronization, because that's the difference to the video you saw before. The fireflies and the metronomes have the same frequency. In this parlance, they would have the same power. But in power grids, you have generators and consumers having different powers assigned to them, or injected or drawn powers, okay? So what do you need to have stable grid operations? I'm sorry, it's a bit cut off here at the end. But anyways, so you have the power flow that is just a function of the phase difference, sinusoidal function of the phase differences. The frequency synchronization can be described as a steady state of those equations if you enter a co-rotating frame that spins with 50 hertz, okay? This makes things easier mathematically. And in order to have stable grid operations, you should have frequency synchronization in all of the rotating machines, but also you shouldn't have too large phase angles. If you have too large phase angles, the power transmitted between 2 oscillators may be too large for the line connecting them. So this line may be cut out, and you would have cascading failure as a very likely consequence. Okay. Now, this is the same equation, but with one added term. This added term accounts for fluctuations added by the inclusion of renewable energies. What happens if you add wind parks and solar farms into your energy mix? Well, you have a fluctuating input. Okay, and as Joachim Painke showed very well, you can compile statistics on this input. Okay, And you should account for this when considering grid stability. But you also should account for the grid topology. You have different transmission grid topologies in different countries. Now you could just stop there and simulate this. You could. This is a system of n. N is the number of elements in a system, typically 300, 400. Coupled elements, and it's a highly nonlinear dynamics. Okay, and then you could perturb the system or a certain node j with a certain noise, and you could record the wiggling around the synchronized state at a given node. This would be simulations. I have a very unhealthy obsession with closed forms in collective dynamics. So I'm looking always for some conceptual gain in those through those kind of forms. So what I'm trying to do is I try to analytically describe what's going on. Okay, I try to find an expression for the grid susceptibility with respect to input fluctuations. Come on. That's it. Thank you. Okay, to do this, let me just go back to some basic physics. Imagine a damped harmonic oscillator. So it's a spring with a mass in a viscous fluid, and in the underdamped regime, which you get when you choose a certain combination of parameters here, the oscillation of the oscillation of the mass is damped, and then at the end, the steady state is just a zero amplitude. Okay, it's resting. Now, what happens if you force, if you put some kind of little forcing on this mass here? Well, you take the equation of the harmonic damped oscillator, and you add a kind of forcing term on the other side. Okay. What you can do here is, if you suppose that you choose a very small forcing term, and if you're not far away from the equilibrium value, you can describe the system trajectory, so x in this case, as a sum of previous fluctuation terms. So you go back until the in history of the forcing, and you have a weighted summation of the fluctuation terms. And the weights in those summation are called the linear response function. And this linear response function is a very characteristic measure of the system's susceptibility to small fluctuations. Okay. To make things easier, usually you switch into Fourier space, which is dynamic equations are usually formulated in the time domain. It's very intuitive, but you can also switch to the Fourier domain, where you look at the spectral composition of a signal. You have the frequency components that you record. Okay, and if you Fourier transform this side and this side, put it in here, or rather put this in here and then Fourier transform, you will get here. You will have an expression of the linear response of the system through any given input fluctuation. Okay. Now, where do you want to go? Okay. So you notice that this is it's a complex function. The real part gives the in-phase response to an input fluctuation, the imaginary part, the out-of-phase response. In the following, I will just consider the absolute value of it, right, which gives you a kind of overall response to the system. To give you an idea, it's just a proportionality factor here. So you, through linear response, you can say that the frequencies act independently. You can say that the frequency component of the signal given by this term is attenuated or amplified by this factor here. So this is why it's very useful to know the linear response function, and you can find an equivalent in psychology. For instance, psychologists compile psychograms of people, so they identify very characteristic traits, and then knowing those traits, you can kind of predict how those persons react to perturbations or forcing by the environment. Okay, and this is what we're trying to do in the power grid. We try to identify a psychogram of the power grid in order to know what kind of arbitrary input fluctuations it's susceptible to. Okay, I won't bother you with all the math. I just tell you that we go from the initial coordinate, which are rotating phases, to an x coordinate which gives me the deviation of oscillator J from its synchronized state. Okay, and doing our business here, we end up at this equation, and this equation tells you the following: on the left-hand side, you have the linear response of oscillator J in my network to input fluctuations at arbitrarily chosen nodes of any number, and then you have the prefactor here, which is the linear response function of the network. So you will see that, and this is a closed form expression. I can, if you don't believe me, I can walk you through this at the end of the talk. And so you have an exact idea of if you put noise at an arbitrary number of arbitrarily chosen nodes in the network, how this wiggling of the phases, or how this input perturbations propagate through the network, and what amplitude in the wiggling of the phases of the phase of an arbitrarily chosen oscillator it causes. Okay, so this is the power of the method. And so I think one of the last slides already. So we try to check, or we can check this. We take a regular random graph, which means that it's a graph that has that is randomly connected with one constraint, that every node has the same number of neighbors. Okay, this is our power grid. You see the red dots are supposed to be generators, and the blue dots the consumers, and the gray lines the connections between them. So I've chosen here node number 3, generator number 3, as the source of input fluctuations. Okay. Now let us concentrate on panel B1 and B2. What happens in panel B1? What can you see there? Well, in B1 you see the near field response, the response of oscillator 3, 35, and 56 through input fluctuations at oscillator 3. So the black curve here would be the frequency resolved linear response to input fluctuations at 3 itself. Orange would be the response at 33, and the green at 56. You can see several things here. First of all, the response at the perturbed node is largest. Okay, it's kind of plausible. You can also have, you see non-trivial peaks that are the result of the connections of the network. Also non-trivial peaks at the perturbed node, because in fact, not only is is oscillator 3 directly reacting to perturbations, but also perturbations propagate through the network and return and influence the wiggling of oscillator 3 around its equilibrium value. This is why also here you have non-trivial peaks. Now, if you go to panel B2, you go to the far field, which means now we are looking at how the perturbations propagate through the network and what kind of response they evoke at those nodes. So the black curve would be the frequency resolved response of generator 17, and the other two curves, the ones of 87 and 41. So you see that if those perturbations propagate through the network, the response here is smaller by a factor of 3 or 4. Well, it's plausible because through the propagation there is some dampening in perturbations. Okay. Okay, this is basically all I want to say about this. Maybe you can ask other questions about the other graphs later on. So to give you the idea of the significance of this term here, in fact, in power grids, I want to have a look at angular stability, which means that if I have a synchronized state and if I introduce a perturbation at a randomly picked node or many nodes, I want to know by what amount the phase wiggles around its equilibrium value. If the wiggling is too strong, then phase differences to neighboring oscillators may exceed a critical value, and the power flow along this line may exceed the critical value as a result. so that the line may be be cut, and then you would have cascading failure and total catastrophe. Yeah. So just as a summary of the program, which is not really a finished, it's not a finished project, it's work in progress. We've the idea is that we take any grid topology, and we want to have a closed form local measure for angular stability. Local because we can go at every node and identify what kind of frequency, perturbation frequency it's susceptible to. Yeah, okay. So for that we look at the synchronized grid susceptibility to arbitrary but small input fluctuations. Joachim Peinke has talked about the importance of intermittency, which means that the input perturbations may also attain large values, okay? So this, for now, is not considered yet. What we obtain is a frequency-resolved measure of any node susceptibility to fluctuating input at an arbitrarily chosen node, okay? So, and it's closed form. It's maybe complicated the bigger the network is, but it's a very long string of a function of omega, the frequency component of the input perturbation. So with it, we can identify vulnerable nodes, optimal nodes for fluctuating input. So we may be able to know where best to place a wind park or a solar farm in order to not perturb the system too much in terms of angular stability. We can also identify harmful frequency components that we may be able to filter out with high-pass, low-pass, band-pass filters that can be seen as storage elements, or they could be realized as storage elements. And we could also propose robust grid designs, all of which we haven't done yet, okay? Just to tell you. Limitations. I haven't considered voltage dynamics in Joachim Peinke's model. He does so. It may be important in some circumstances, but negligible in others. I have assumed uniform machine parameters, so every machine has the same damping torque and the same inertia. But you can vary this. Then you have to do things numerically. Right? It gets a bit more complicated. I've considered the small fluctuations regime, because I have applied the method of linear response, but in fact the linear response is just the first term of something called the Volterra expansion. So you can also do a nonlinear response where you consider also a second or third terms, okay? This is possible, but it's also much more work involved, and whether things can be done analytically, I don't know, I don't think so. We haven't yet, you can consider input cross correlations, but in the paper whose address should appear here, we haven't considered this. It's an archive paper. Yeah, and in fact, we just have considered temporal fluctuations on the level of autocorrelation, so two-point correlation functions. We haven't considered how the probability density function of the random variable that presents the fluctuating term is transformed through the propagation of the perturbation through the network. So, but it's in theory it's possible, but we haven't done this. With that, I will thank you for your attention.
Okay, we have time for a few questions. We start down there because it's closer.
I have a question for the correlation function, the K, if you could.
The K, yeah.
Or the kappa, yeah, where you define it. So
yeah.
Before.
This would be here. Before. The way that I define it would be.
No.
In the simple case. Okay.
Yes, key. Yeah, here. So it's a Lorentzian function.
Yes. Yeah, but here yes.
Yeah, because I don't understand the. Because in many particle physics we get the same equations to describe interacting electrons in a solid. But then, so you have your Lorentzian function with a lifetime, and then the broader it is, the more interactions you have between the particles. But then if to resolve that, that's really difficult because you don't get somehow a closed equation. You would have to sum to infinity all the terms.
But my
So-
network is
and that's
is
why,
finite.
but then I wonder why your it's not particles, but I don't know, your perturbations do not interact. And then if they don't interact, it should be delta functions and not have the broadening. But then if you go...
What kind of perturbations should interact? Sorry.
Yeah, the perturbation there, your...
Okay, here.
Yeah.
Yeah. Do you mean the frequencies should interact, different frequencies? This would be the nonlinear response.
No, because you see it, because it's a Lorentzian function and the lifetime is given by the term after the e, the imaginary part.
Yeah.
And then you see that also then in your results. So you have broadened functions and not delta peaks. So there is some interaction. But then how do you resolve that analytically? So
I haven't understood which kind of interaction. Sorry, I'm a bit sick today. Yeah.
I mean, I try to make the analogy between many particle physics and your, because it's the same equations, but I don't know.
All I can say is that
I just wonder why it's closed, and because we have to sum up to infinity, and that's impossible. Because if you want to get your key, then you can express it as Green's functions, and then the Green's functions, to make it correct, you have to sum up to infinity. And
I don't need to do this, because it turns out that if I do a diagonalization of a matrix that I'm using, I will end up at so I choose different coordinates, and then I diagonalize the system.
Yeah,
And this gives me a function that is that describes a linear, damped oscillator, harmonic oscillator, but in different coordinates. And then I back transform. So, but for this system in different coordinates, this is just coupled. This is not even coupled. This is uncoupled harmonic oscillator, damped harmonic oscillators.
So it's uncoupled harmonic oscillator.
In the new coordinates. That's
yes,
the beauty.
No, but that's then the important approximation, which then makes it solvable.
Yeah.
Okay.
We have time for another question.
Okay. Thank you for your talk. You just, at the end of your talk, you mentioned that maybe, with this, you could for a given grid, say why it's best to put, for example, a solar farm, for the grid. Well, no. What about having, we are in the trend of having more and more prosumers, people which produce their own electricity, and that will be very tiny additions, but nodes. But when it develops, you could imagine that it at the end turns to be significant. Could it be also addressed with your model, this, or I don't know?
In fact, we also have experimented with turning generators into consumers, prosumers, right? But I can't show you any results. Yeah, I wouldn't be able to say you from top of my head how this translates into, or how do the results differ with the inclusion of those prosumers. But we have played around it a bit numerically, and it wasn't very stable numerically. I remember this, but we haven't fully explored this idea. Yeah.
Okay, thank you. We move on. No, I'm sorry, we have to move on. So now you're going to talk about financing renewable energy.